All right, so in this video, we want to take a look at an idea that I'm going to call, well, or the textbook I use calls diminishing returns. So here's the deal. Let's jump in. This all stems from a question like this, which was actually for our student class on our homework, for our sampling distribution summary homework. And someone asked me a question, and I was like, oh man, I never taught how to do that. Now, maybe you came up with a cool strategic way to figure it out by manipulating sample size to get this answer. But so what we want to look at today, and what you're seeing here, right, of course, you can pause the video to read this in more detail. But in this situation, right, we're changing our sample size, and we want to think about what effects does changing our sample size have on the standard deviation of a sampling distribution. So this idea of diminishing returns. We know that increasing our sample size decreases the standard deviation of the sampling distribution, right? We took a lot of time to explore that with our applets, looking at the range with the Reese's Pieces applet or the means applet, right? With all the blue bars dropping down, we could create two simultaneous sampling distributions. And we could see that the sampling distributions based on a larger sample size had less variability, right? We're more squished together, right? So that's a general idea that we absolutely have to know, right? N goes up, standard deviation of a sampling distribution goes down. And over the next couple of weeks, we'll also connect this idea to what we know about confidence intervals, margins of error, and the widths of intervals. But so what we want to do in this video is we want to kind of quantify that. Quantify kind of if we increase sample size, how much of an impact does that have on our standard deviation? And that's how we're going to approach a question like this. So when we're talking about sampling distributions, right? We know our sampling distribution for, so let's see, sampling distribution for proportions. We know the standard deviation is the square root of P times 1 minus P all over N. This is the standard deviation of the sample statistics, right? A sampling distribution, we imagine we take a sample, find P hat, plot it, and so on. And for the sampling distribution for means, hopefully you're already thinking to yourself what the standard deviation formula is. We know the standard deviation is sigma over the square root of N. And this would be our standard deviation of the sample means. So for this idea of diminishing returns, our ultimate conclusion is true for both types of sampling distributions. Let's just focus using this formula because it's a little bit simpler. And let's just assume sigma is 1, just to make our life easy. So here's what we want to look at. We're going to pretend sigma is 1. We know we're working with the formula sigma over the square root of N, which can become 1 over root N. Let's say that N is 4. If that's the case, the standard deviation of the sampling distribution, notice I'm really trying to make a conscious effort to not just say standard deviation, but the standard deviation of the sampling distribution is going to be 1 because we're pretending sigma is 1. I just picked that number for the sake of simplicity over the square root of 4. And so our standard deviation becomes 1/2. Now, what we want to think about is if I increase the sample size, let's say I take a sample that is 9 times bigger. So now my N is 36. What happens to the standard deviation? Well, now for my standard deviation of my sampling distribution, I have 1 over the square root of 36, which is 1/6. And so the question is, what is the relationship between this and this standard deviation? Right? We got to know some stuff about fractions here. Hopefully we all know 1/6 is smaller than 1/2, but specifically, how much smaller? And now that you've paused and thought about that, right? Like you might think to yourself, we could do 1/2 times 1/3 would give us 1/6. And hopefully we're comfortable enough with fractions. Multiplying by 1/3 is the same thing as dividing by 3. And so to recap, what happened is, if we took the sample size and multiplied it by 9, the standard deviation ends up being divided by 3. Why do you think that's the case? And what is the relationship between these two numbers? Hopefully you have an idea. Let's take a look at another made-up example and see if we have that same relationship. So let's pretend that our n is, right, we're still assuming sigma equals 1. I'm just making that up just to pretend. So let's say n is, I don't know, 10. No, that's a stupid idea. Let's say n is 100. And 10 wouldn't be good because I don't know the square root of that off the top of my head. So now I end up with 1 over the square root of n, or in other words, 1 over the square root of 100, which is 1/10. So the standard deviation, if n equals 100, the standard deviation is 1/10. Now let's say we take a sample that's 4 times larger. Let's say n equals 400. Then my standard deviation becomes 1 over the square root of n, or the square root of 400, which is 1 over 20. And so now again, we want to compare what happened to the standard deviation. N got bigger, so the standard deviation has to get smaller, and it did, right? Sample size went from 100 to 400, got bigger, standard deviation got smaller. How much smaller? Well, 1/20th is half of 1/10, right? You could think of that as 1/10 is the same thing as 2/20ths, so this is half of that. Or you could think to yourself, 1/10 times 1/2 is 1/20th. And that's the same thing as taking 1/10 and dividing it by 2, cutting it in half, right? But ultimately, the takeaway we want to see here is, if we take our sample size and multiply it by 4, the standard deviation of the sampling distribution ends up being divided by 2. So to recap, we get a sample that's 4 times bigger, the standard deviation gets divided by 2. If we have a sample that's 9 times bigger, the standard deviation gets divided by 3. And hopefully, maybe you hypothesized initially, this is the square root of 9. And this is the square root of 4. So as we increase the sample size, the standard deviation does get smaller and smaller, but increasing sample size has a diminishing impact on how much we decrease the standard deviation of the sampling distribution. Really, I probably should have done these examples in a backwards order, because what I'm saying is, if we take a 4 times bigger sample, that'll cut the standard deviation in half. But if we take a sample that is 9 times bigger, that'll only divide the standard deviation by 3. And you might think to yourself right now, what if I took a sample? What's happening to my pen? What if I took a sample that was 16 times bigger? The standard deviation would only get divided by 4. For instance, if I wanted to get a standard deviation that was 10 times smaller divided by 10, I would need to take a sample that's 100 times larger. And the idea here is, whatever we multiply the sample size by, whatever factor we increase the sample size by, the standard deviation is only going to be divided by the square root of that value. And that's because regardless of whether we're working with means or proportions, this n, right, I could split this numerator and denominator up separately. Either way, this n is underneath that square root, inside that radical symbol. And so increasing n decreases the standard deviation, but only by the square root of what you multiplied the sample size by, which I feel like I said pretty poorly. We could prove that algebraically, right? Like if I just have sigma over the square root of n, if I want a sample that's 25 times bigger, now I have sigma over the square root of 25n, which is the same thing as sigma over 5 root n. And so we can see here, this is the same as this. Our standard deviation is just getting multiplied by 1/5 or divided by 5, right? So we could do some algebra to kind of prove that rule. So to recap, main idea that we want to take away, right? Like you could have just ignored the whole video and just memorized this at the end. Of course, that's not what we're trying to do. But so if I take a sample size that is 81 times bigger, what's my standard deviation going to get divided by? If I take a sample that's 36 times bigger, whoops, my standard deviations, what's that going to get divided by? Right here, it's going to be divided by 9, or 1/9 as big. Here it's going to be divided by 6, or 1/6 as big as the original standard deviation. And again, that's the square root relationship. Now, if we go conversely, let's say I take a sample that is 16 times smaller. Well, now we have to think the opposite. If n goes down, the standard deviation is going to go up. How much is it going to go up by? The standard deviation is going to be 4 times bigger. Why 4 times bigger? Because 4 is the square root of that 16. So that's this idea of diminishing returns that we're working with. That's all comes back to the square root that's around the n in the denominator with both the sampling distribution for means and proportions. And so to finish up, try this one out. This one's on your take-home test thingy, quiz, whatever it's called. So we've got 500 students trying to determine the most popular song in 2020 amongst teens. We got a different sample of 125 students. What happens to the standard deviation? So our original n was 500. Now we're going to a sample of 125. Now, when we want to think about how much this decreased by, we want to think multiplicatively. We don't want to think like, oh, it's minus 375, it's 375 people smaller, right? We want to think, what did we divide by? So to get from 500 to 125, we're dividing by 4. Now, in this situation, n is going down, which means the standard deviation of the sampling distribution is going to go up. So that means this is out, this is out, this is out. So worst case scenario, even if you didn't know what you're doing, as long as you know n goes up, standard deviation goes down, n goes down, standard deviation goes up, right? You're going to be able to narrow down your options pretty reasonably. And the standard deviation is going to get bigger because the sample size got smaller, but it's not going to get 4 times bigger because of that square root in the denominator. It's going to get 2 times bigger because we take the square root of this 4. And so that's the idea here with diminishing returns. Increasing sample size has a diminishing impact on how much it decreases the standard deviation because of the square root. And of course, we could always flash back to our old friend, square root of x. And we could even see, right, as x goes up and up and up, there's a diminishing, right? The y value is still increasing. This graph's still getting higher and higher and higher. But the larger the x value, the less of an increase in that y, right? We can literally see visually with this function that diminishing impact of increasing x on the effect of the y value. Just in case you missed some algebra.